VLSos here. This is a video lesson on using a Riemann sum for area under the curve. For example, we could be given a function such as x squared minus 6x plus 13. And we could be asked to find the area under f on an interval, in this case from 4 to 12. Now, from a previous lesson, we know that we can translate an area question into sigma notation. And when we do, it's called a Riemann sum. A Riemann sum is using sigma notation to generate an estimate for an area under the curve. In general, from a previous lesson, the area under a function from A to B is sigma with an indexing variable, often starting at 0 and going up to 1 less than the number of rectangles, which would produce a left-hand estimate with an argument delta x times the function evaluated at the lower bound of the interval plus delta x k, where delta x is equal to the upper bound of the interval minus the lower bound divided by n number of shapes or rectangles that we're going to use. So let's apply that. Now, there are many ways to produce the estimate. We could choose different shapes. Again, we're going to choose rectangles because that's the formula that we're prepared for in this notation. But we could also choose a certain number of rectangles to use. In this case, I'm going to give a couple of examples. We're going to do 2 left-hand rectangles. When we do, because the number of rectangles that we use affect delta x, we need to calculate delta x to be the end point of our interval minus the beginning end point of our interval divided by n number of rectangles, which is 2, makes our delta x, 12 minus 4 is 8 divided by 2 is 4. And of course, this is going to produce a very crude estimate, almost useless. But for practice, then sigma would start at a k value of 0 for left rectangles up to 1 less than n times delta x times the function evaluated at 4 plus 4k. The function is quite sophisticated, so I got to be careful that when I produce the argument in sigma notation that I'm getting it correct. I'm going to first put in my a value plus delta xk and then square it. We have a second term in the function, which is 6 times, again, that a plus delta x k, and then plus 13 to finish the function. Checking my parentheses, this last one closes this. Technology would probably be helpful to evaluate that, though you're only going to apply the argument twice because you have an n value of 2. Let's give one more example of changing the number of rectangles to be 24 and having them be right-hand estimates. Delta x would be then calculated as 12 minus 4 divided by 24, or 8 divided by 24, that reduces to a third. Sigma notation then starts at 1 because we want to skip the first function value. The first left value is at k equals 0, so the first right value is at 1, and we go up to n, which is 24. The argument then is delta x, or in this case 1/3, times a plus delta xk is going to be expressed as k divided by 3. 1/3 k is the same thing as k divided by 3, all squared, minus 6 times that same a plus delta xk plus 13. And this parenthesis closes this first one. This sigma notation would probably require technology or a calculator to use. Processing this by hand would be tedious to get correct.